Hey, thank you for the introduction. I should say that all of this is joint work with Antoine Chambert-Loir. And if the title seems a little mysterious, if you have never heard of divided powers, I think that's very normal. So I will not assume that you are familiar with this. Instead, I'm going to start with some motivation to show up where these come up in mathematics and why we are interested in formalizing them. Then I will give you the formal definition of divided powers, and I will discuss the main points of our formalization. And while doing so, we'll see that to do one part of this formalization properly, we actually needed some results from topology on multivariate power series rings. And these were not previously available in Lean, so we also added them. So I will give you a quick overview of these results. OK, so for the motivation, I want to start by considering two simple examples. So for the first example, suppose that you have a polynomial, so some finite sum of the form an times x to the n, where the an are real numbers, and you want to compute an integral or a primitive for this polynomial, then the formula for one primitive will be given by the sum of an over n plus 1 times x to the n plus 1. Now you can again take this primitive and integrate again. If you do that, you end up with n plus 2 times n plus 1 in the denominator. And if you keep doing this, you end up with some large product of integers. There's a second example that's kind of a similar flavor, and this has to do with the exponential power series. So we know the exponential function e to the x. We can write this as the infinite sum of x to the n over n factorial. And in particular, if you take a real number a, and you substitute a times the variable x into this power series, you get the infinite sum of a to the n over n factorial times x to the n. Now, in both of these examples, I started with considering real numbers. But often in mathematics, we want to generalize things to other settings, right? So it's a very natural question whether we can replace the reals by something else here. And in order to do that, first, we can make the observation that both of these questions are related to the family of maps, x goes to x to the n over n factorial, which at this point, I'm thinking of this family as maps from the real numbers to the real numbers. But as I said, we may want to replace the reals with some other ring. And in some cases, this is very easy. So for example, you can start by taking, instead of the reals, you can take the rational numbers. And everything still works, because you can still divide by n factorial for any n. Or by the same reasoning, you could take the complex numbers or polynomial over q, or really any q algebra. Any ring where you can divide by non-zero integers, everything was fine, just taking the same formulas. But you might be in a situation where you don't you are not always able to divide by non-zero integers, right? Like if you are working over the ring of integers, for example, in general, this x to the n over n factorial is going to be a rational number. It's not going to be an integer. And the same thing will happen if you take other rings, like, for example, the ring of p-adic integers. So this might complicate a little bit the question of trying to understand the exponential map, for example, in these situations. But Cartan realized in the 1950s that even if this family x to the n over n factorial is not defined, if you cannot divide by n factorial, you can replace it by some other family, which we are going to call a family of divided powers. And I'm denoting this by gamma n of x here. And this family is going to have the same kind of properties as this family x to the n over n factorial. And this is possible even if you are working in a ring where division by integers is not possible. OK, so where does this show up in mathematics? Well, one situation where this comes up is in modern research in arithmetic geometry or algebraic number theory. So there is one ring, BCRIS, which is used by people working in these areas. I'm not going to define the ring BCRIS in this talk, and you don't need to know the definition to follow this. But I want to highlight some of the applications of this ring. So one application is there is an area of number theory called p-adic Horst theory, where you want to understand p-adic Galois representations. So in this area, the ring BCRIS can be used to detect certain Galois representations that are the so-called crystalline Galois representations. So representations that have some interesting property. Then the second problem where this shows up is that if you have a nice algebraic variety defined over some p-adic field, There are several cohomology theories that you might want to study associated with this variety. And a very natural question is, how are all of these cohomology theories related to each other? So in particular, there is one comparison theorem between the étale cohomology and the crystalline cohomology of such a variety. And this comparison theorem also involves this definition of the ring decrease. The definition of the ring is very complicated. If you were to unfold all of the details, this takes over 100 pages of mathematical research, so no textbooks, but like really research articles. Yeah, as I said, we don't need to know the details of the definition. I will just say that the definition has many steps, and one of the steps is to take the divided power envelope of a certain ring. Again, we don't need to know what the divided power envelope is. We only need to know that this is some universal construction that relies on the theory of divided powers. So if we want to be able to have a complete formalization of this ring decrease in Lin, so that we can keep then formalizing research in arithmetic geometry, one of the first things that we need to do is to develop the theory of divided powers, and that's what we do in this paper. Sort of an overview of the history of divided powers is given here. So as I've mentioned, they were introduced by Cartan in the 1950s. And actually, his motivation was not from arithmetic geometry. He was studying a problem in algebraic topology. But then most of the proofs in this area are due to Roby in the 1960s. And the construction of this universal divided power envelope that I mentioned in the previous slide was done by Berthelot in the 1970s. And Berthelot also developed the theory of crystalline cohomology. Now, 50 years later, we are formalizing this theory in Lin. Okay, so let's make precise. I said before that divided powers is just a family of maps that behaves like x to the n over n factorial. And that's exactly what this is, but this is made precise by these 7 axioms. So we are going to start with a commutative ring A and an ideal I inside A. A divided power structure on the ideal I is a collection of maps from the ideal I to the ring A, indexed by the natural numbers, satisfying these properties. You don't need to read all of the properties in detail, but I will discuss some of them. The way that these properties are derived is just by looking at the properties of the family x to the n over n factorial and then abstracting them. So for example, x to the 0 over 0 factorial is equal to 1. So in the first condition, we are going to ask that gamma 0 of x is equal to 1. Similarly, x to the 1 over 1 factorial is equal to x. So we ask gamma 1 of x is equal to x. And then, for example, if you look at the 4th axiom, so this explains how divided powers behave with respect to sum of elements. Then, well, if we were to do that with the family x to the n over n factorial, we end up with the formula x plus y to the n over n factorial. We use binomial expansion, and then we reorganize the terms. And we end up with some formula that looks like this. Yeah, so again, the rest of the formulas are just a summary of how the family x to the n over n factorial behaves with, for example, scalar multiplication, multiplication of divided powers, or composition of divided powers. If we have a triple composed by this commutative ring A, the ideal I, and the family gamma, we are going to call this a divided power algebra. In this slide, I have the Lin formalization of this definition. And if you are familiar with reading Lin, you see that this follows quite closely the previous slide, but there are a few differences. So I'm going to focus on the differences between the two definitions. The first one is that in the informal definition, I ask for A to be a commutative ring. But in Lin, we actually allow A to be a commutative semi-ring. So we don't require that subtraction is defined in A. But we still require commutativity. And this is because divided powers have always been studied in commutative settings. And it's not clear what the right definition will be in the non-commutative setting. So we don't want to relax that hypothesis. A second difference between the definitions, here I said that the divided power structure is a family of maps from I to A. But in the formalization, instead, we have a family of maps from the ring A to the ring A. And then we have one extra condition that for every element that is not in the ideal, gamma n of that element is going to be 0. And then in all of the other properties, we impose, where needed, the condition that the elements are in the ideal. The reason we do it this way is to avoid having to coerce explicitly the elements of the ideal to elements of A, because that gets annoying, especially when you are considering several ideals at the same time. Okay, yeah, there are a couple more comments. So first, in the definition, well, in the property that explains how this behaves with respect to the sum, we have this sum over pairs of I and j adding up to n. So in Lean, that family is called anti-diagonal. So yeah, in this depot add condition, we have the sum over this anti-diagonal family. And then the last comment about this definition is this uniform bell function that appears here. This is this kind of combinatorial looking element. And just looking at this formula, this might look like a rational number, but in fact, we can prove that this is always a natural number, and we did that in the formalization. Okay, and so I've already discussed most of this. I will just add that we proved that for every element A in the ideal, n factorial times gamma n of A is equal to A to the n. Okay, now once we have the definition, the first thing that we did is to formalize some examples that are interesting. The first example is if your ring A is a Q algebra, so if you can divide by n factorial, then actually the family x to the n over n factorial is the only divided power structure on any ideal that you want to consider. The second example, which is interesting for number theory, is you take A to be the ring of p-adic integers, and you take the ideal I generated by P. Again, we saw that there is a unique divided power structure on this ideal. And to prove this, what we need to check is that in the p-adic integers, the fractions p to the n over n factorial are always divisible by p. So these are always going to land in the ideal P. And then the third class of examples that we considered is that if we take a ring A where n minus 1 factorial is invertible and some ideal I such that I to the n is equal to 0, then again, this family x to the n over n factorial is going to provide a divided power structure on the ideal I. So some particular cases of this are if A is a ring of characteristic P, or more generally, a ring where the prime P is nilpotent, then you can take any ideal where I to the P is equal to 0, and this will work out. Or for any ring A, if you have an ideal where y squared is equal to 0, then x squared will be 0 for every element in the ideal, so you can always take this family of divided powers. Okay. We can also define morphisms between divided power algebras. So if we have divided power algebras given by A, I gamma, and B, J delta, a divided power morphism is a ring homomorphism from A to B, such that the image of the ideal I is contained in the ideal J, and such that this map is compatible with the divided power structures on both sides. So that means that delta n composed with F should be the same as F composed with gamma n whenever you apply it to an element in the ideal. Yeah, so this is just the Lean definition. We just encode these two properties as fields in the definition. And we proved several facts about divided power morphisms. For example, the composition of divided power morphisms is again a divided power morphism. Or if you know that the ideal I is generated by some family of elements S, you don't need to check the compatibility condition in all of the elements of I. It's enough to check on the elements of S. We also have a notion of subdivided power ideals. So this is just going to be a subideal J of your divided power ideal I, such that whenever you take an element x in J and any positive number n, gamma n of x, again, is an element of J. We provide two versions of this definition in Lean. So one is the propositional version. So is sub divide the power ideal? So that will be saying that you have an ideal J, which is given as data, and then you impose these two conditions on the ideal. And this is the version that is more useful when you are working on some larger proof, and at some point you have to prove that some ideal that appears in the proof is a divided power ideal. In that case, it's more convenient to work with this unbundled version of the definition. But for example, we also provide the bundled version, so the version where you have the ideal together with these two conditions, because, for example, we wanted to prove that sub-divided power ideals form a complete lattice, and for this, we need to have the bundled definition. We proved many properties of sub-divided power ideals. This is only a subset of them. But for example, again, if we want to check that the span of S is a sub-divided power ideal of I, we just need to check some condition on the generators. We also study divided powers on quotient rings. So we prove two lemmas to prove the equivalence that the intersection of J and I is a sub-divided power ideal of I, if and only if there is a divided power structure on the ideal generated by I in the quotient A mod J, such that the quotient map is a divided power morphism. Yeah, and then we also prove some relation between divided power morphisms and sub-divided power ideals. So if you have a divided power morphism, then the span of the image of the ideal I is a sub-divided power ideal of the ideal K in the image. And the kernel of F intersected with I is a sub-divided power ideal of I. The last interesting construction that I want to discuss is how to put a divided power structure on a sum of ideals. So suppose that we have two divided power structures on two ideals I and J of the ring A. And moreover, we know that these structures agree on the intersection of I and J. In this case, we can prove that the sum of the ideals has a unique divided power structure that extends both of the structures on I and J. And we provided two versions of this construction in the Lean implementation. So I will explain why. In the first implementation that we did was just starting with the observation that any element in I plus J can be written as X plus Y, where X is an element of I and Y is an element of J. And then using the properties in the definition of divided powers, that forces gamma I plus J of this sum to be given by this formula. Now, we formalize it like this, but there are a couple of problems with this approach. The first problem, I mean, not really problems. These are things that we could do, but they are not very nice to do in Lean. First thing is that this decomposition as X plus Y is not unique. So we have to prove that if you choose a different decomposition, you still get the same value. And then once you have defined things like this, you still have to check that all of the properties, all of the axioms in the definition of divided powers are satisfied. And this involves a lot of computation. It's not very nice to do. Yeah, so there is a second implementation, which is actually our preferred implementation. And this is more elegant mathematically, and it relies on the observation that if you have a divided power structure gamma I, on the ideal I, this is going to induce a map, a linear map from the ideal I to something called the exponential module of A. And if you take this, the two maps that you get like that from I and J, they are going to give rise to a unique linear map from I plus J to the exponential module. And this unique linear map is going to determine what the divided power structure has to be on the sum of I plus J. OK, so the reason that we did not do this from the beginning is that the exponential module was not available in MATLib. And actually, to define the exponential module, we needed to add a lot of results about topology of multivariate power series rings, of which the library didn't have anything. So power series rings were available, but only as abstract rings. We didn't have anything about the topology. So in the last part of the talk, I will just briefly summarize some of the results that we added. First, I will start with the definition of this exponential module. And for this, we will first say that a power series f is of exponential type if f of 0 is equal to 1 and f of x plus y is equal to f of x times f of y. And then the exponential module of A is just going to be the set of all of the power series that are of exponential type. Now, the way that we relate this to divided powers is that if A I gamma is a divided power algebra, then for every element in the ideal, the power series given by the exponential of AX, defined by this sum of gamma and A times x to the n, this can be proven to be of exponential type. If you remember the first slide of the talk, there we were talking about the classical exponential series from analysis. And in that case, we had a to the n over n factorial times x to the n. So this is a direct generalization of that formula. And the way that you prove that this is of exponential type is really by the same argument that you will use in analysis with the classical series. OK, now the map that sends an element A in the ideal to the exponential of AX is a morphism of A modules. OK, so this is the theory. The obstacle to formalizing this in Lean was this equality that we have here. So we have to impose that f of x plus y is equal to f of x times f of y. X and y here are variables, right? So if you wish, they might be variables in a polynomial ring or maybe in some power series ring. And f is just some power series, which is an infinite sum of elements. So it's not always possible to substitute some element of a B algebra into a power series. And in order to make this possible, we have to develop the topology of these rings. So first, if we start with a ring A that has a topology, and we have some set of sigma, which is going to be the set of variables and might be an infinite set, then the ring of multivariate power series, where the variables are indexed by sigma, is naturally induced with the product topology. And we provide this as a scope instance in Lean, but not as a global instance, because there are other topologies that might be interesting in some cases. But if you endow this power series ring with the product topology, it's going to inherit a lot of the topological properties of the ring A. So for example, some of the properties that it inherits are being Hausdorff, being a topological ring, meaning that the ring operations are continuous, or being a complete uniform space. And in the latter case, we also obtain that the polynomial ring with variables indexed by sigma is dense inside the same power series ring. OK, so the last thing that we need to discuss is how we made possible this f of x plus y is equal to f of x times f of y. And for that, we need to be able to substitute multivariate power series into other series. So let's take A to be a topological ring, B to be any ring with a map from A, and sigma, again, the set of variables. We know that we can always evaluate polynomials in any family of elements of B, because polynomials are just going to give us finite sums. But to evaluate power series, we actually need to understand the topology. So I'll just very quickly say that we need the topology to be linear. So this is something that was not available in MATLAB. We added the definition of linear topology for ring and modules. And then evaluation of power series is going to be possible if you are evaluating in a family that doesn't make the series go to infinity. So for example, when the set of variables is finite, you just need all of the elements to be topologically nilpotent, which again is a notion that we formalize in Lean. We provided this formalization of evaluation of power series. And as a special case, you can obtain substitution of multivariate power series. again, with certain hypotheses. This is not always possible. You need to guarantee that the series is going to converge. But in one easy case where this converges is if the set of variables is finite and the series where you are substituting all of the terms, all of the elements in this family have constant coefficient 0. This is the simplest case. Then you can substitute. And this is exactly what happens in this formula, right? We are substituting x, y, and x plus y. All of these have constant term equal to 0, so this is well defined. And yeah, this is everything I wanted to say. Thank you very much.